The next one is Anova testing. Okay, we'll start with the case study so that we will make it more interesting. Okay, Anova stands for analysis of variance, and this technique was developed by R.A. Fisher in 1920s. Okay, so far we discussed about comparing the two populations: independent sample t-test, paired t-test, matched. It is also called the dependent t-test or matched t-test. Okay, all the terms are same, and some cases they call it student t-test. Student t-test. Don't get confused. That is nothing but the t-test only. So in the case of previous test, like two independent sample t-test, paired t-test, we can compare up to only two populations. Okay. If you wish to compare the means of more than two groups, you cannot use t-test, hypothesis t-test or z-test, right? So because of the limitations. So those tests are meant for either conducting single sample t-test or two independent sample t-test or paired t-test. But if you want to compare more than two groups, you cannot do it with t-test. That's when the Anova test comes into picture. The Anova test, we can use it to test whether the means of more than two quantitative populations are equal. Or more than two populations, the continuous variables are equal. Okay. So now the question is, why can't I use the t-test, two independent sample t-test, to compare the means with more than two groups? The flip side of conducting multiple t-test approaches, for example, there are three populations out there. Just give me a second. Look here, in this case, you have three different groups you want to compare it. For example, North region, South region, East region. You want to compare the means of these three regions data. These three regions are nothing but three independent populations. So in that case, you draw a sample here. But if you have to use the two independent sample t-test, first you need to compare these two. First, you need to compare these two. You need to perform a two sample t-test for this one. And then you need to compare these two. And finally, you need to compare this one with this one. Okay, it's something like A and B, and A and C, and then B and C. You need to compare this one. So how many tests you need to conduct in this case? This one, right? 1 and 2, and comparing this one is 3. Three times you need to run the two independent sample t-test. You need to compare the pairs only. You can compare only the pairs. You cannot compare multiple groups means at a time using two independent sample t-test. It is pretty clear. If I use it, what is going to happen? See, but in the past, there was nothing called Anova test to compare more than two groups. They were using two independent sample t-test only. So if I do it, what is going to happen? So in that case, what will happen? Look here, in this case, your first hypothesis, the x1 bar for your first population, which is nothing but first population sample mean, second population sample mean, are they same? And alpha value. So this is what your null hypothesis. You are assuming that these two are same. There are no statistical difference exists between the sample mean of your population 1 and population 2. And the alpha value is 0.05. And similarly, h sub 0, x1 bar, your population 1 sample mean with population 3 sample mean, you are going to compare it. Okay. The alternative hypothesis is h here, obviously, x1 bar not equal to x2 bar, x1 bar not equal to x3 bar, x2 bar. So in this case, you are supposed to conduct 3 independent sample t-test. 3 times you need to conduct. If you have 3 groups, and if you have 10 groups, now assume that how many number of times you need to do, right? So in this case, the issue is, look here. So what is your, if alpha value is 0.05, what is the confidence level? So 1 minus, you know very well, the area under the curve is 1. 1 minus alpha, which is nothing but 0.95. Since you are conducting the test 3 times, 0.95, your confidence level is decreasing. 0.95 into 0.95 into 0.95. Your values are, and right, and if you subtract this 85.7 plus, so if you from 1, your significant value also getting reduced, the alpha value also getting reduced, right? So hence the two independent sample test is not much helpful in this case. That's when they came up with something called Anova test, there are different types of ANOVA tests you can do it. The one-way ANOVA and two-way ANOVA. But within the two-way ANOVA, we have something called two-way ANOVA without replication, two-way ANOVA with replication, and we have something that's called three-way ANOVA and analysis of covariance, ANCOVA, MANOVA, and MANCOVA. Likewise, different types of tests are available under the ANOVA test itself. Got it? Multiple tests are there. Okay. So in this case, what we'll do is, MANOVA stands for multivariate analysis of variance, and MANCOVA stands for multivariate analysis of covariance. Okay. ANOVA stands for analysis of, ANCOVA, analysis of covariance. What we will do is, we are going to focus on one-way ANOVA and two-way ANOVA. Rest of them, let us not focus on this at this moment. Probably if time permits, we will see it later point in time. Because now we need to focus on the Python part next session, and then we will proceed with, once we are done with Python, we'll jump into the machine learning model. That's very crucial. Okay. Fine. To start with, let us understand what is ANOVA. Let's okay, before we proceed with it, let us understand what are the assumptions that it make. Like z-test and t-test, the populations from samples were obtained must be normally or approximately normally distributed. This is the same for all kind of tests. Sample must be independent. This is also same. The variance of population must be equal. In the case of ANOVA, the variance must be equal. Okay. But it is not all the time equal. Okay. Let's probably, right, we can slightly ignore this one. Okay. And next one is, how do we define the null and alternative hypothesis? Because here we are comparing more than two groups. So the null hypothesis, obviously, your population mean for all the groups are same. That is what we are hypothesizing it. And the alternative is, at least two of the means are not equal. At least two of the means. Maybe these two means are equal, but these two means are not equal. And in the case of t-test, we have used the test statistic, x bar minus mu divided by small s divided by square root of n. That is called your t-test statistic. But in the case of ANOVA, instead of saying t statistic, here f statistic. The test, the formula is different here. It is little bit different, but if you concentrate here, it is very much simple. But hence, I request you all to please concentrate the formula to understand the f statistic. Okay. Supposing I have gathered the data from 3 different retail stores. Let's say I'm running 3 retail stores in Chennai. One is in Adyar, other one is in Thiruvanmiyur, other one is in, let's say, Velacheri. In all the stores, I have taken, so many, 3, 6, 7, 8 days, how many number of units we sold. That is the one we noted down. I noted down here. Okay. Probably it's a mobile store. Okay. I'm running mobile phone store, retail store. And I just noted down in each location and each day how many. For the last 8 days, in each day, how many units I sold. And then each store, what is the average units sold? How many 7 mobile phones that I sold it on an average in each store? I computed it here. And if you take the grand mean, if you take all the values and if you find out the mean, that will fall somewhere here in the middle, right? It will fall somewhere in the middle. And for store 1, let's say the store 1 is your store 1, store 2, store 3. Okay. Let's do one thing. Let's say your store 1 is this one, and your store 2 is this one, the mean, and store 3 mean is this one. The 23 is falling in the middle, and whereas the store 1, for this, the average sales is this one. And then for store 3, if you plot it visually, right, to view this visually, it will be something like this. If you look at here, the X2 bar, the store 1 and store 3, the average sale is far off from your grand mean. But the store 2 mean is falling exactly in the middle of your population. The grand mean and the store 2 mean is almost overlapping. If the sample mean of your store is far away from your mean, too much of difference is there, then this sample mean did not come from this. Sorry, this sample did not come from this population. That is what we can make out. And let us focus currently. Okay, don't get distracted. Look here. This is the F statistic formula. In this case, your grand mean is there in the middle, and your retail store, let's say your store 1 and store 3, right? The store 1 mean is somewhere here, and store 3 mean is somewhere here, and the grand mean is here. Okay, let's say in this case, yeah, you have something here and something here and something here. Okay, 3 different means, but the grand mean is falling here. Okay, so in this case, the distance from grand mean. So we are very particular about the distance from variability between and among the means. So here the F statistic formula is between, right? How far the means are, between the grand mean, and then divided by each sample. For example, each sample mean is falling here. Let's say this sample mean is somewhere here in the middle, and this sample mean will be there somewhere here, and this sample mean will be there somewhere here. Right? Each sample mean is here. So now this is sample mean is there in the middle. The grand mean is there in the middle. Okay. And here, in this case, what we are doing is variances between and variances between. How far, for example, you have one value here, right? So you have one value. How far this value is away from this mean, right? Variance, this is called variance within. How far each sample is away from your grand mean. So variance between and variance within. So variance between and variance within, that is what we can see, right? So the grand mean is equivalent to variance between the samples, how far each sample mean is away from the grand mean, and how far each values are away from, each sample mean. You understood? The variance between the sample and variance within the sample. Okay, how much it is. That is what this formula does. Grand mean is equivalent to variance between divided by variance within. Very simple, isn't it? So instead of saying this, between and within. So F stat is equal to between and within. How far each sample mean is away from this one. It's something like your income, average income is how far away from your population mean. That is called your variance between. Let's say this is your family, right? Each sample is your family. Within your family, let's say, more than one person is working in your, in your family. In this case, what is the average salary in your family? How far your salary is away from your family's average salary? So this is variance within the family, variance between the family. So your family and the other families, right? Variance between your family and other family, and variance is within. So variance between and you just think that way, okay? So that is how it works, the formula. Okay, so like I said, the one-way Anova, it is also called a one-way analysis of variance, can be thought of as an extension of your t-test for independent samples. It determines means of more than two independent groups significantly different from one another. So in this case, we are comparing more than two groups. If you have to compare more than two groups means, then obviously you have to use the Anova test. And it uses only independent variable or factor of 3 or more than 3 groups. Dependent variable is measured variable, which means or being compared. Okay. So in this case, the dependent variable and independent variable. Okay. The independent variable, let's say you have 3 groups, north, east, west region, right? 3 different groups, total sales, or 3 different stores, means average sales want to compare it. Okay. So independent variable can have 3 groups. And dependent variable is a measured variable, only one variable, okay? To realize the one-way Anova is an omnibus test study, it cannot tell you which specific groups are slightly different from it. But since you are comparing more than one group, this test will not tell you which group is statistically different from each other. For that, you need to conduct something else called post hoc test, very simple one. Only thing is the terms are a little bit difficult to understand, post hoc test and Anova test and all. Otherwise, it's very simple one. Let us start with a simple case study, the real life scenario. Just give me a second. I'm getting a call. So in the case of retail industry, right? So take for a Walmart or any retail industry, right? Optimizing the shelf placement is crucial for maximizing sales and enhancing the shopping experience. For example, look here. So let's say you go to mall, right? You go to a retail, shop, big retail shop, and inside that, these are the shelves, right? They kept each and every item in different places. Shelf placement. The shelf placement, keeping the items in different places of the shelf matters a lot. Okay, and here, by keeping the right product at the right place, it can maximize your sales, and at the same time it will improve your customers experience. Hey, whenever I go to the shop, I can see all the items which I most frequently buy, or it's available at your eye level itself. Better I'll go and buy it there. It's very easy to track, which items are there where. Okay, so in this case study, what we'll do is we'll check the impact of different shelf placements on product sales using the Anova test. Okay, so using the test, Anova test, we will find out if there are statistically significant differences in sales among product placed on different shelves within a store. If I keep this item here, how much sales am I going to get? If I keep this item here, how much, item, for example, cosmetics item, all right? So cosmetic items on the face, moisturizer, if I keep the moisturizer, and if I keep, for example, your foundation stuff, and if you want to keep your lipstick and everything somewhere here, right? The female items, cosmetics, if you keep all the thing here in different places, does self position has any influence on the sales? I repeat this, does keeping the items in a specific location of the shelf has any influence on my sales, whether it is increasing my sales or not? That is what we are interested in this scale shape. Okay, for example, in a specific retail store, they want to determine whether the placement of a specific product on different shelves affect its sales. So for example, you want to keep the cosmetic items, you keep it here, somewhere here, and you wanted to find out, if I keep it here, does it increases my sales? Or if I keep it in the bottom shelf, or if I keep it in the middle shelf? Top, middle, and bottom shelf. So if I keep this, specific products in this top, bottom, and middle, does it has any impact on sales? See, something like that. Let's say you are a retail manager. Okay, you're a retail manager. Okay, you are a retail manager. You wants to understand, and you are a retail manager. You want to understand. Let's say you are a retail manager. You call the different retail chains. Okay, let's say you are owning a 3 retail stores. You are running a 3 retail stores, and you are calling 3 different retail stores, A, B, C. Okay, and then you tell them, the managers, hey, you keep all the cosmetic items at the top shelves in your shop. Okay, for the next 10 days, you are not going to change the space. And at the same time, you are calling another retail store manager and you're telling, hey, keep all the cosmetic items in the middle shelf. Don't change it for the next 10 days and don't give any special offers, any discount. The same instruction you gave it to all the 3 different stores, but in the third store, you are telling them to keep the cosmetic at the bottom. Okay, at the bottom. And then you give them the same instruction. So, right, keep all the items, but each store, they keep the same cosmetic item, different places. And next 10 days, they are not going to give any special offer, any discount. Okay. And then what you do is, after a while, what you do is you call them and then you note it down. Okay. You call them, each manager of the 3 different retail store, and then you ask them. So because this retail store, you told them, you gave them instructions very clearly, keep all the cosmetic at the top, and then you give me the numbers, how many units you sold, and keep all the cosmetic in the middle shelf and give me how many units we sold, right? You call the store 1, store 2, store 3 managers, and then you note it down, and at the end of each and every day you call them and you note it down how much you sell. But obviously, when you see this one, front shelf, right? So you have something called front shelf. When you keep these items in the front shelf, the sale is more compared to other two. That is what we can see it here. What you do is all the three retail stores, how much sales you made. You first, note, you take all the values and you find out the average sales. Then you find out the variance. What is variance? Sigma squared. You remember the standard deviation we discussed that time, right? If you take the square root on the variance, that is what your, if you take the square root on your, so if you square the standard deviation, that is what your variance. We can say that also, right? So for you take all the three locations, unit suit, and then you take the average and then you find out the variance. Okay. And then the next step is what you do is, and each group and each store, you take the average unit store. Okay. And then each store you find out the variance in each store. Okay. You find out the variance within each store, and you found the average within each store, and then you found the average grand mean. This is your grand mean, this is your grand variance. And then if you add all the values, how much you get? 22 plus 18, 30, 40, 54, right? And similarly, if you add all these values, you get, this is the one is, this one, 54. And 203.3 is, so in this case, 203.3, how did I get this? So in this case, we are trying to find out the variation between groups for this group, and this value you are trying to find out. Sorry, and so you're subtracting the mean from each and everything. Sorry, not this one. And this one you have varied it by variation between groups. Now you are finding out the variation. For look here, in this case, you are 4 minus 8.3, and you do it that way. And look here. So here I'll just show you here. Okay. And so how I got this one? 54. You add these values. You add all these values, you get 54, right? And the sum of squares between groups. So here, squares between groups, this is what I'm talking about. So 4 minus 8.3 squared plus 8 minus 8.3. Sorry, okay, you need to subtract the mean from the grand mean. Okay, that is how you get the sum of squares between groups. See, this is the one as sum of squares within the groups. Sum of the squares within the groups. The 22, 18 plus 14, that is what is sum of squares within groups, and variation between groups. Here, what you do is, one second, I'll just clear all the things. In this case, 4 minus 8.3 whole square, and then 8 minus 8.3 whole square, and 13 minus 8.3 whole square, and you get something like this. And you need to multiply this by 5. Okay, you need to multiply, because this is nothing but your sample size in each group, right? So 5. So 40.7 into 5, you get, this is how we get this value. This value is little bit different, because here within the group variance, sum of squares within groups. Okay, 22 plus 18 plus 14 is 54. But whereas in this case, variation between the groups. Okay, here the mean of each group, you need to subtract it from this one, right? 8.3 minus 4, or 4 minus 8.3 squared, and then whatever the value you get, you need to multiply this by, because in each one you will have the 5 samples, you get this one. So 203.3 plus 54 is equivalent to this value. It is coming out clearly, right? The left-hand side is equal to the right-hand side. So in this case, the formula is, like I've discussed a while back, the sum of squares between groups, between divided by within, right? Within. So here the between sum of squares between groups is how much? 203.3 divided by 2. The degrees of freedom, right? So degrees of freedom is nothing but the sample size. Sample size is 3 samples, top, mid, shell. 3 samples, 3 minus 1 is 2. And this 203 is for your sum of squares between groups. Sum of squares between groups is 203.3. Sum of squares between groups divided by the degrees of freedom is 2, because we have 3 groups. 3 minus 1 is 2. So that's why you're getting. So 101. And sum of squares within group. So in that case, 54, right? This is the one comes here. And then here all the 3 groups put together. How many number of samples are there? 5 into 3. 15 minus 3 is 12, right? So 4.5 will get. So sum of squares between groups divided by sum of squares within group, you get the final value as 22.7, 20.59. This is what for the degrees of freedom 2, 12 of your F is equal to 22.59. So this is what your F statistic value. Now the question is, what is critical value? How can I find out the critical value? So in this case, there is something called F table. So if you look at this table here, and here the degrees of freedom in the numerator is 2, and the degrees of freedom in your denominator is 12. Can you see that? So degrees of freedom in the numerator, degrees of freedom in the denominator. So here this is the numerator is 2, denominator is 12, and where it intersects, so the degrees of freedom, the numerator degrees of freedom is 2 here. And I say, look here, they mention it, degrees of freedom in the numerator. Oh my God. So degrees of freedom in the numerator divided by degrees of freedom in the denominator. So look here, even in this table, they mention very clearly. The numerator value degrees of freedom is 2, and the denominator degrees of freedom is 12. Where it intersects these two values, that is what your critical value. So 3.89. So the critical value is 3.89. Got it? So now if you look at visually, this is what your F distribution. F distribution is something like this. It is something like, right skewed. And your critical value is 3.89. Your critical value is 3.89, right? And what is your F statistic value? Your F statistic value is 22.59. Now you tell me 22.59 is greater than your critical value 3.89 or less than 3.89. It is obviously greater than, because 22.59 is a bigger number than this one, right? Hence it is falling in the rejection region area. Your F distribution will something, that looks something like this. It's a right skewed one. We know the critical value. This is the cutoff value for your rejection region area. From here, the rejection region area starts. Since 22.5 is more than this one, is falling in the rejection region area. Hence, we are rejecting the null hypothesis, and we are going to conclude that the sales, whatever we made, is not same across all the shells position.
Hello.
Top shelf and
Hello.
Yeah, who is this? Hello.
இந்த இது பிராட்பேண்ட் ரீசார்ஜ் எப்படி பண்ணணும்னு சரி அது இதுல பண்ணிட்டேன் கூகுள் பேல
Can
பண்ணிட்டேன்
you please go on mute, guys? Yeah, sorry. Okay, I'll just mute you on.
அதுக்கப்புறம் தான்
Okay, so this is the one, right? So hence we are rejecting the null hypothesis. What do we conclude now? We conclude that the sales, the groups, right? The whatever the sales we made, right? So across the 3 different shell position were statistically significantly different from each other. The units sold were statistically significantly different from each other. Here, the null hypothesis is all the cell position values, mean values are same. Look here, the null hypothesis, all the 3 groups mean values are same. Alternative hypothesis, it is not same. Since the F statistic values greater than the critical value, we are rejecting the null hypothesis, and then we are concluding that the 3 groups mean sales values or the mean units sold were statistically different. This is what we can do. So this is pretty simple, right? Yeah, because in this case, the table is available here. With that, I can, and also interpreting this table is pretty simple. Degrees of freedom in the numerator, degrees of freedom in the denominator. Where it intersects, what is your degrees of freedom in the numerator? So that is your 2 here. See, ideally, actually this formula is something like that. This one, the entire thing is there in the numerator, and then this entire thing in the denominator. So numerator, obviously the degrees of freedom is this one, the denominator degrees of freedom is this one. So the degrees of freedom for the numerator is 2, and the degrees of freedom for denominator is 12. And if you go and check the numerator, look here, this is what they mentioned very clearly. Numerator degrees of freedom, and the denominator degrees of freedom is 12, right? 2 and 12. So where the 2 and 12 intersects? Here. 2 and 12 intersects here. So hence it is 3.8, and this is what your critical value. Like I said, instead of using the critical value technique, we can use the p-value. Look here, it's very simple here. In this case, 2A Anova with, let me do one thing here. Fixed processing. Okay, let me just. Okay, in this case, I did not write anything here. What I will do is, let me check here. I think 2-way Anova with replication test of. Okay, what I will do is, I will just write a script here. Don't worry. But don't worry too much about the command, everything. I'll explain you later point in time in detail. At this moment, you just simply watch what I do. Okay. All you need to do is just note down. All you need to do is just note down the p-value. Okay. You need to tell if the p-value is less than alpha or not. And import, we have something called SciPy, scientific Python, SciPy dot stats as stats. Here I just say something like a data, and I'm going to use something called the dictionary. The curly braces, something called dictionary, and the top shelf and the key value pair. Okay. The dictionary, we have something called in Python, there is something called dictionary. The dictionary, you will find something called key value pair. In this case, how much value that I'm using it here? Yeah, 23762. Okay. In this case, they say the top shelf is 23762, right? 23726, 23726 top shell, and the middle shell, similarly the middle. Yes, Aishu, just give me a second. Okay, I will. So once I'm done with that, I will explain. Okay, 10 comma 8 comma 7. This is pretty simple, right? Yes, Aishu, you are correct. Middle shelf, and let's say, this is your bottom shelf, not the bottom, front shelf. I just say front shelf. Why you are putting semicolon? This is the question from Praveen. That is for key value pair. In dictionary, you need to specify the key value pair. The key and value pairs has to be separated by colon. Okay. And front shelf 10 comma 13 comma 14 comma 13 comma 15. We are done. Okay, I have defined the data set. I'm going to hit the run button. Invalid syntax. Top shelf and invalid syntax, front shelf. Okay, here, look here, single quote. Okay, not double quote. So probably they can eliminate these kind of things, right? One second. What I see here is front shelf is the problem. Line 4. Escape. You can press escape and L to see the line. So this is where it says, okay, here I put the the comma, right? Now no issues. And let's query the data and see. And this is how the data looks like. Okay, I'm going to convert the data frame. So I just say df is equivalent to pd dot data. There is something called data frame. I'm going to wrap this one by data frame. Okay, and then I'm going to put so that you can see something like a table columns, right? Rows and columns. You can see something like that. 23726. Look here, 23726, 10, 8, 7, 5, 10, and 10, 13, 14, 13, 15. We are done. So my data set is data frame is ready. Next, there is something called f underscore one way. This is a function that is available. So this function returns two things: f statistic, comma p underscore value is equivalent to scipy. You remember I have used something called scipy package. In this package, you have the statistical functions, right? Or any statistical test you want to do it. So that package consists of all kind of functions. This is f one way Anova. And here what I do is I'm going to say the top shell, three groups. I'm going to, because we are comparing the means of three different groups. And in this case, the middle shell, and the third one is your df, and here I just say front shell. And yeah, so we are done with this, and I'm going to run this. Let's see. Yeah, the scipy is not defined. Why? Okay, in this case, sorry. Okay, scipy dot stats is correct only, right? Okay, here instead of scipy, I'm going to say stats because I mentioned it is an alias as stats, right? Correct. I just click on this. Next one is I'm going to use the print function. Anova results. Anova results, and print f statistic. Yeah, I will share it. Don't worry. Soundarya, I will share it. Don't worry. Okay. The script, right? Yeah, last week I did not share it. I will share it without fail tonight. Okay, don't worry. Print and p hyphen value. See, last week I thought of uploading this in our website, but anyhow, I'll share it to you also. Okay, I'm going to. Okay, so if you get something, that means you have put unnecessary quote around it. Look here. What is my p value? Is this less than alpha? Can someone tell me? Is this less than alpha? Yes, you're all correct. Correct. Right, you're all correct. How about others? Most of them are missing from today's session. Okay, here in this case, the p-value is, if you see here, right, it ends with e minus 0.5. That means you need to prefix with 0. It's nothing but 0.0008, the rest of the values. Look here, if I type this value and if I run it, look here, it is equal to this one, right? So this is nothing but this value. This value is obviously equivalent to 0. Since p-value is less than alpha. What is alpha? 0.05. Since p-value is less than alpha, we are rejecting the null hypothesis and we are going to conclude that the mean, the average units sold in each location is not same. It is statistically different. Hence, we are rejecting the null hypothesis. In this case, what is the null hypothesis? Mean, each group mean is same, right? All the three shells mean units sold was same. We are rejecting this null hypothesis. We are going to conclude that the average units sold in all these three shells are not same. It is statistically different. That means shelf position does matters in terms of increasing the sales. If you hide your items, you just think that way. If you hide your items, right, the frequently purchased item, if you hide it, if it is not visible to the customers, how they can find out, how they can buy it, right? The most frequently purchased items, at least, right? And if you can keep it in the place, the prominent area in your shop, that can attract the customers to buy more. So the front shelf, which means as soon as they walk into your shop, And if these items appears to their eyes, obviously they can buy the products. That's what we can make out from this one. And the next one is, okay, how do I, so this one, in this case, we are rejecting the null hypothesis, and we are going to conclude that the average units sold in three different places or position of shelf are not, or statistically different, fine. But how do I find out which group has statistically, which pair of group has statistically different means in it? So that's where we have something called Tukey honest significant test. There is something called Tukey honest significant test, using which you can compare, you can do the pairwise comparison. For example, I just go here and then I just in this case everything is ready. For example, I want to key result. In this case, sales, right? And let me do one thing. Here I have used okay, I just say sales, comma, shelf position. Yeah, is not defined. Okay, in this case, here I need to go and import another stats models. Here some more stat models and stats dot multi-comp. There is something multi-comp. Import pairwise to key HST. Sorry, this is from stats models. Import that one. Okay, and then I just go ahead and execute this one. In this case, yeah, it will throw an error because sales is not there. Honest test here. Top shelf and middle shelf. This is how I've given it, right? That's the problem here now. So what I will do is, in this case, I'm going to define it something different way. I take the same data here. I just say sales. 2, 3, 6, all the things. Okay, I just put everything here. Okay. And then 10. See, we can do it in the other way around, but I wanted to show you what are the different ways that you can display the data, okay, or store the data. And here I just say shelf position colon. Now I say top shelf. This is another way of doing it. Top shelf and into 7 plus no, in this case 5, right? Into 5. 5 times repeat the same thing, okay? The top shelf, you repeat it 5 times. That is what it tells. In this case, this is your middle shelf. Middle shelf into 5 plus and here front shelf into 5. So I'm going to execute this one. So it is not equal. Mistakenly I plus sign and then execute it. Again, syntaxes. How come here? Shell position. Yeah, here I did not specify comma. Bad operand type unary into 5. Here I did not. How come I missed 5? Okay, now it is working fine. In this case, what I'll do is shell position. Capital S. See, if you see the data, right, you can use different approaches also. This is what, look here in top shelf, how many times? 1, 2, 3, 5 times, and the bottom shelf, these are the things. And here the sales is not getting displayed along with this. Yeah, the sales is this one. Okay, and let's do one thing. Shelf position. If I do this, no, the sales, key error sales, nothing sales is available here. 1 second. So 5 times. This is 3, 5, and for this 5, middle shelf and front shelf 5. Okay, yeah, that's what I was wondering. So why the sales is not made as part of this one? Shelf position and this one. But if I use the other way around, right, it is causing problem there. Let me try. So what is the problem? Everything is correct. 2, 3, 7, 2. It's all correct. Colon, top shelf into this one. Cool. Everything is same, right? Okay. And at the end, I put the comma here. Shell position, but sales is not displaying the way how we expect it. Bottom shelf, everything is correct, but it is not coming out clearly. Okay. What I will do is here, I will convert this a data frame. That's the reason why it is getting confused. PD dot data frame. And now if I do the df data frame, yeah, this is what, this is how I want to organize the table. Very good. It is doing good job. Now, if I click on run, and it will work, and you want to see the two-key result, it gives you the something like this, right? Two-key result. And we need to plot this one for this interpretation. If you want to interpret this, for example, what I do is I just say for group 1, comma group 2 in two-key result dot underscore multiple multi-comp dot pairwise. See, you don't have to worry too much about this. Everything I have given this one here. Okay, I remember everything. And what I do is reject. I put something like reject is equivalent to key. But if you use another start, it's like a SAS and all, you don't have to write this much of code. Okay. Multi-com. But you can also reuse my thing because you don't have to write too many lines of code. And here I just say group 1 and group 2 comparison. If you want to do it, I will write it here. I will print your string comparison between group 1 and group 2. Okay, and next one is, okay, I just execute this. Okay, end of line. Okay, here I did not specify the colon here, right? That's the problem. There is no attribute multi-comp. To key result dot to key underscore result dot underscore multi comparison. There is a spelling mistake there. And multi comparison is now there is no issue here. And the issue is here it shows multi comp. multi-comp dot pairwise comparisons to key result dot let me do one thing. And shortcut way is to key result dot, and if you do pairwise multi-comp dot pairwise comparison, it is coming out clearly, right? You don't have to type it. I just put it here. Sorry, I just replace this one here in the for loop. No attribute pairwise comparison, multi-comparison. And sorry, group 2 in group 1, group 2 in. A lot of syntax mistake. Bear with me, guys. Okay, there is no pairwise comparison. There is something wrong here, the pairwise comparisons. For group 1, group 2 in to key result. Correct only, right? Multi-comp pairwise. I think I need to import this one here. Stats models dot stats dot multicomp pairwise to key HSD pairwise multicomp is correct only because you remember when I just typed the to key result dot, when I press tab, look here, you just type this up to this. If you type it, that is enough. And then if you type the underscore and press tab, look here, multicomp dot, press tab, it give you the code completion feature here, right? So here multicomp. Do we have, can we see any pairwise comparison? Oh, here it is not there. Multicomp, wait, I just make it pairwise comparisons is there, right? I think in this one, it is not available. All pair test. What I will do is, yeah, we will take the Tuki HST otherwise. Tuki AHSD. Method object is not iterable. Yeah, for this one, it is not working. Okay, this one probably I will check and tell you. So in this case, what happens is it will compare, it will do the pairwise comparison. For example, top shelf mean sales and middle shelf mean sales, and then middle shelf mean sales with the front shelf. See, with the advantage of the Anova test is you can compare more than one pairs means, more than one pair mean simultaneously, but you cannot do it two independent sample t-test, right? So, but with Tukey honest significant test, we can compare the mean for all the groups. Sorry, we can compare the pair, we can do the pairwise comparison. So that's the reason why you mentioned it very clearly, pairwise comparison, pairwise comparison. But unfortunately, the pairwise comparison is not working here. Here, let me give it a last try. Otherwise, let's not waste time. I will check and tell you tomorrow, right in tomorrow's session. Pairwise comparisons. We can use the help also here. This is what the help side. Multi-comparison to key HSD results. We can use to key HSD results also. Let us give a try the last one. The sandbox.sats multi-compare. Okay, this is just a thing here, but they did not give any example here. The package name is that one. Pair wizard. Likewise, you can do that. To key HSD, where the hell? Pairwise data. This is your R language. Okay, this R language, not Python. Yeah, Aishu, one second. I'm just thinking about it. Okay, what else we can? I'm there. Okay, I'm just thinking at what could be the reasons and how we can fix it. But I'm sure this is the one I used it. Pairwise to key HSD. The result it is, yeah, that is the one. We'll hold this one. Or else we will do one thing. To key result. Okay, what I'll do is I'll just add the thing here. And here, best thing is I just use multi-comp. Okay, multi-comp is equal to multi comparison. This is another option, okay, comparison of your DF sales, comma, DF shelf position. I am going to sort the results. Results is equivalent to multi compare dot to key AHSD function. This is another way of doing it. Okay, and multi-comparison not defined. So in that case, multi-comparison, I need to import that one here also. Cannot import name. Multi COM. Okay, this is capital C. Here it is case sensitive, guys. You need to be very cautious. Look here, it is working fine. And here multi comparison. Okay, here I gave it correctly. But however, right, so the says key error sales is missing here. And here I just give it fine. The sales is there here. Yes, it's correct only. And here, yeah, now it's giving correctly. To key result, yeah, very good. And here, oh, in this step only we are posing that issue, right? Yeah. Key error sales. Oh, okay. I did. So look here, the sales, the column, first letter is supposed to be shelf position, not self position. Spelling mistake. Now it's working fine, right? And the next step is on the results. What I'll do is I'll just simply remove this one and then I'll try with the results. Let's see what happens. It is not showing anything. Only thing is we need to put it in a for loop, okay, to get the values. What I will do is I'll just go ahead here and then I'm going to use a for loop and pair dot reject in zip. I'm going to zip is to combine the results. Okay, don't worry about all the things. Okay, you can simply reuse this one as a template for your thing. Pairwise comparison, and then the we have something called result. Okay, the result is there. You can use the results also here. The results dot reject comparison, square bracket, comma, the results dot reject, and then the colon tells us where the body starts, and this is where the body starts. Group 1 comma group 2 is equivalent to pair. Okay, print comparison between GR1 group 1 and group 2. That's all, guys. We will see if this is must be integers or slices, not string. Shelf position is correct only, but here the pair reject, pair comma reject in results table, pairwise comparison. And the results, wait, I'll do one thing, results, and then the p-values. Yeah, we can get the p-values here. This is what the p-value for, the 3 groups. We can get it here itself, right? Data, DF total, and groups. Let me do one thing. Top shelf, middle shelf. And then let's explore something more. Data and DF total groups. Yeah, mean difference. Look here. This is what I want to find out. So here, between the top shelf and middle shelf, what is the mean difference? And from the middle shelf to front shelf, what is the mean difference? And then from the top shelf to front shelf, what is the mean difference? So which one has more difference? The first one and the middle one, right? First one and top and middle shelf has significant difference. At the same time, the top and okay, we want to see the -5. Look here, if you see here itself, you can find out, right? So 4 minus 8, how much? 4. 8 minus 13, how much? 5. Sorry, 4 minus 8, 8 minus 13 is 15, and 4 minus 13 is how much? 9, right? -9, correct. So the top and the front shell, if you see it here, the 4 minus 13 is how much? 9, right? -9. And 4 minus 8 is -4. This one and this one. And then -4 and 4 minus 13. That is your 4 minus 30 is now 9, right? So 4 minus 8 is -4. 4 minus 13 is that one. And -5, how did I get it? -5. A minus A, B, and 8 comma 30. Yes, correct. 8. And this one and see. Here, 4 minus 8. For these two group, what is the mean? So -4. And this one and this one, how much? -5. You get it here. And this one and this one, 4 minus 13 is -9. Which group has more difference? 4 minus 13, right? The top shelf and front shelf. These two group have significant difference. That means the shelf top is if you keep the items in the top shelf, it is not much helpful. Keep it in your front shelf. That is what the common sense tells us. So here we can see the differences more, right? Whichever shelf in this case as significant, the pair of cells, we need to compare the pairs, shelf top and this pair, compare these two pairs mean value. 4 minus 8 is -4, but between these two, not much difference, right? And between these two, the difference is there, but this one and this one, the difference is more. Hence, compared to all the things, right? This one is more difference. Hence, you can keep the items in the front shell. Got it? That is what we can interpret from this. So this one itself made our job simple. This is your one-way ANOVA test. So this is called your honest signaling already exists. Okay, ANOVA 1. This is called your honest significance test. Okay, 2K honest signaling, using which this is also called the post hoc test. Post hoc. I just write it here. Post hoc test. Using post hoc test, you can you can compare pairwise mean. Okay, A to B, what is the difference? And B to C, what is the difference? And A to C, what is the difference? That is what it gives us. And which one has significant difference? This is the one, -9. So the top and front shell has significant difference. Hence, if I keep the items in the front shell, obviously the sale is more. Hence, keeping the items in the front shell does influence my sales. In the sense it improves my sales. So this one concludes the one-way ANOVA test. Okay, in this case we are comparing more than 2 groups. So with this we are able to conclude that with the F statistic value or the p value, since the p value is less than alpha, rejected the null hypothesis, we conclude that the mean units sold across the shells are statistically different. It is not same, it is statistically different. And then we did the post-hoc test. With the help of the post-hoc test, we are able to find out which pair has significant difference. The top shell and the front shell has significant difference. Hence, if you keep the items here, it really makes sense. What is that? What is your question? So why -9? Why can't it be minus? Obviously, the difference is too high here, right? Aishwarya. Hmm. Okay. No. See, we are comparing. We can make the pairwise comparison using ANOVA post-hoc test. That is really good. With a single test, you can compare, the more than one pair. The same thing without reducing the confidence level or without increasing the significance level, we are able to conduct the test here. That is the takeaway here. Yeah, here the -9 tells us, look here, the -9 tells us the 8 minus 13 is how much? 5. And 4 minus 13 is 9, which means we are able to sell 9 more items on an average in front shell compared to your top shell. This is how technically we can conclude it. So or the other way around. Okay, if you keep the items in the top shell rather than in the front shell, our sale is going to decrease by 9 units on an average. Sale in the sense, the unit of sales, right? Unit of items, quantity, number of quantities will get decreased by 9 if you keep it in the top shelf instead of in the front shelf. Hope it clears. Okay, good. Yeah, fine. See, usually we don't conduct manual test. It's all available. But when you attend the interview, we do not know, right? So nowadays, online test is there. They may give the table like this, and they expect you to interpret this table also. Okay, that's the reason why I explained you. But in the real life, in the real world scenario, this is pretty simple. Which one? The test. If you conduct the test through the software. Okay.